I'm going to still okay, before the first speaker of the afternoon session, good afternoon everyone. Irene is going to give some direction about the proceeding of the conference. Please, Irene.
Yeah, we're going to publish the proceedings of the conference on la Revista Mexicana de Astrofísica. It's not a new journal, we're 51 years old. And as an announcement, the next release of cloud is appearing in our November number. The new editors of the Revista, of the main journal, are myself and Carlos Roman. Silvia Torres is still the editor of the Memorials, which is called MMX-AZ. And I want to announce to you to know that an open access, it's a digital-only journal registered everywhere. There are no charges to individuals or institutions. It's in all the editorial platforms of the globe. And the Revista Mexicana of Astrophysics is referee. Here is the web platform. We have a new face. I leave you with it. About the proceedings, the editors are going to be Omaria, Erika, Jacob, and myself. We have established the review talks will be 10 pages, main body text and figures, unlimited pages of references. The contributed talks will be 4 pages, main body, and unlimited number of references. Posters will be 2 pages, few references, please. And the deadline for submission that we have established is December 15th of 2020. Okay, here is the overview macros of the Revista, and we are going to expect many of you to contribute to this effort.
Thank you, Irene. And now I welcome the first speaker of the afternoon session with Konrad Tristram, who will talk about the interplay of accretion and outflows in AGN in a Parsec scale.
So thank you for the organizers for giving me this opportunity to present this work, speaking of this wonderful place. So this work I'm going to present here is the contribution from these collaborators here. So I'm going to, and now it's not working. I see it. So what I'm going to show, I think I'm showing you this image here of Multiphase, of course, from Bada and Sumi, I think the 4th time at this meeting, because I want to emphasize that probably this region of around 1 parsec to 10 parsecs, which we are trying to understand the vision processes of the supermassive black hole, actually look significantly more complex than just a simple donor picture that has been around for so many years. So, what if we want to study this region? So, historically or originally, this has been done mainly by population studies looking at type 1 versus type 2, and by SED thinking, as we have also seen earlier this week, with the problem that the issue that these SEDs and both the models and also the data give quite some ambiguity of structures that are on these scales. So if you actually want to go and observe such these Parsec scales in the years, we have to go to really outside resolutions. But this can only be achieved by chronometers. And there's two chronometers which can routinely do this job. This is in the infrared. Plus emission from these regions using the NTI and the submillimeter as we heard this morning, looking at molecular dust and also the nice. So yeah, I'm going to use this Circinus galaxy, which is probably after 1016, most famous nearby AGN, as a experiment to study the EGN physics in these scales. So Circinus galaxy is a type 2 universe before we have Parsec distance, which corresponds by 1 parsec is 50 milliarcseconds. It has a relatively lightweight supermassive black hole of only 1.6 solar masses. This has been very well determined actually because there's a water laser disk in almost every rotation on the supermassive black hole. So early observations, so I'm going to have a few slides and just repeatedly and send the stage of your observations. So this is just to see what we know from early observations. So early observations with the VNTI of plus emission with the median interferometer was at the time industry construction was not possible, so we had to do this modeling of Gaussian black body emitters. And what we see here is this kind of structure of 3 Gaussian emitters with one component highly elongated with some kind of substructure block, and then another component sitting more as a this component. This was then, we modeled this with JWST, and we modeled this data by using a radiative transfer model for such a dusty torus with composed of a dense disk in the center, and then this hyperpolarized cone, dusty cone shell. This could very well reproduce the SED. I'm going to actually show the SED in both slides from this model, but it also could very well reproduce the photometric data, the visibilities. So if you take the visibilities of this image, it could be very well reproduced, and it could also reproduce the single dish Vizier emission data from the skies. Yeah, now we have a second generation infrared interferometer in the TI, in the mid-infrared, which is the TIS instrument. This is the TIS instrument, which do image reconstruction, as has been shown here by JWST. And we see again this emission in this direction. That's the central block with some substructure more in the east-west direction, and then there's also more extended emission in this direction. That we have this very narrow disk line. This is actually an issue with this data that it doesn't have a full video, which would be other instrument. So actually, this does not appear as strong as the image here. And we can go and compare this to the, for example, to the laser disk, which is now shown here in the center with the blue and red sides. And then we have the radio emission in this direction, and then it's just one goes just over away. And then we have also the larger scale quantization code. So, all, for example, by Travis a couple of years ago. And as you can see, this very nicely sits perpendicular to these the emission is mainly extended into the polar direction. And just coming back to the question, on Monday, actually we see that in this case, 80% of the emission are elongated in the polar direction. accretion and 20% the mid-infrared dust emission is important. Yeah, so now coming to ANMA data. This is the first round of observations were focused on the CO emission lines. First, we'll take a look at the continuum emission at 350 gigahertz in this case here, where we see this kind of structure. I will immediately also show the 690 gigahertz emission. We see this kind of spiral structure here with a strong emission one towards the center. If you want to understand what is causing this emission, the thing that we can do is obviously, this is okay, so I actually wanted to say that I like this so if you want to investigate what is the cause of the emission, you can look at what typical emission mechanisms there are in the submillimeter to reproduce this submillimeter emission. And depending on the power loss spectrum, we say we have either dust emission, free emission, or synchrotron emission. And if we look here at the extended material, we get like flux ratio from 690 gigahertz to 350 gigahertz, around 10 to 20, which corresponds to a spectral index of 3.3 to 4.3. Which is in line with dust emission. So also this extended emission here is from dust emission. But very similar to what was also shown by Santiago this morning, it's clearly seen that in the center there's something else, and we have rather flux ratio of 6, between 2 and 6, which corresponds to a spectral index of 2 in this case. So obviously there might be something else going on here. And to understand this better, we collected the spectral energy distribution of this galaxy going here from the near infrared, mid-infrared, submillimeter, and then all the way to the radio. The blue ones are high resolution data, stars, data cases where the plots almost not visible are larger vision regions. The big one, so if we take this in extended emission, for example, Popeye arm, we get this very steep slope, which is consistent with dust emission. Then I got here actually the spectral energy distribution from the model that I showed slides ago from Marcus Zalewski of this across the cone structure. And as you can see, it very well fits the mid-infrared part. But then it has very steep ranges, the drop off in the submillimeter region. And at that time, I just had some fitted the power off to this region, which has a index of 0.4. We just actually look at this and just say that the millimeter wavelength, there's significant contribution of emission. Now we come to the more recent data. Actually, a student of together with Terry and myself about Bussard work on this. So here you have now the 250 gigahertz continuum map. And again, you see this spiral structure, but now we actually start to resolve theta component, which is actually elongated more into this polar direction. And if we then zoom with very long lines here on the right side, we can see that we actually recover east-west elongated structure, this extended emission here, and then in the very central contours, actually the position angle changes to around 45 degrees. So we also collected now there's significantly more data, so we can also collect the spectral energy distribution here, not only in the submillimeter to radio regime. And what you can see is first the points here for some emission region again outside of the nucleus. This is the red, the light points are the very nucleus, so the inner beam, and then this is the 300 millisecond, which focus on the center. Again, plotted the Zalewski model, so the extended emission is mainly dust emission, but for the innermost, we can actually very nice fit power law of the spectrum mixed minus 1. So our interpretation that this is optically thin, free emission, which is here in the Circinus galaxy, which is an indicator for the outflow. Yes, and we can actually then even do a pixel to pixel. This is my name for B2B decomposition of the extended boost. We have again here the full continuum. Then we decompose in this power law component plus the dust component, and here we see the free component, which is very much centered with possibly slight propagation acceleration. And then as far as you can see, you see that this dust component is for this extended emission, also traces some spiral structure. Okay, let's compare this now, once we have reached these scales, to the dust emission. This is again the image in bit thread constructed from the Matisse data. And we can overplot now the contours from the 260 gigabytes. And actually now we actually do see a relatively good match, especially with also this east-west extension and also some extended material in this direction. So our interpretation of this dust, of this millimeter continuum is that we are seeing here mostly iron minus the outflow component. Bao did some additional massaging of the data using the additional massaging, and there is like this kind of almost zigzag location, and with these two bar-like structures, overplotting down the lasers from Carbon, I think this is the water laser emission. And now if we see that this east-west bar is the cone sitting like this as one of the cone edges, we can actually fit the ridge here and project it inwards towards the laser disk. The same on the other side, and we find this that actually this point where this inward projected cone edge is actually hitting the laser disk is at a radius of 4.16 Parsec. The interpretation is that we are seeing here either the coordination region where the wing is being is being coordinated, or where it's even being launched. And this actually nicely additionally increases where actually the bend in the accretion disk is located. Good. And now final few slides. Yes. I'm going to talk about the molecular classical mechanics. We have HCO 322 and HCN 322. On the left, you see the moment one maps, velocity fields, and you can clearly see the emission is dominated by rotation. However, it's not really super clean disk rotation, so there is some deviation from disk rotation, and we did this standard thing to use a 3D Barolo model of ring fits through the data cube, and you see the model here in the center of these ring fits, and then here on the right you see the residual from this fit. And one can see is that there is a blue residual to the north essentially, and the red residual to the south. And the northwestern side of the disk is the far side of the disk, while the southeastern side is the near side of the disk. And because we only see one velocity component, so it's not several velocity components, but it's clearly one single shift in velocity component, our interpretation is that we are seeing inflow in this region with velocities on the order of 14 parsecs. Yes, on the two slides. The other alternative, so using actually this one region where we have this inflow region, we can actually estimate, assuming the material that we have in the disk, we can actually estimate the inflow rate, which is between 0.32 solar masses per year. We can also do Baroque thing, which is shown here on the left, including the radial velocity component, which is shown here, and combining it with the Yamamoto Nagai disk model, mass and this, we can actually also derive a global inflow rate. Together with this global inflow rate, we get a feeding rate on scales 5 to 10 parsec, and we work 4.3 to 7.5 solar masses per year. We can compare this to the accretion rate of the supermassive black hole, which is only 0.4 solar masses per year, which implies that actually almost 90% of the accreted material is being expelled again before it actually reaches the supermassive black hole, if not more. There is a few measurements of the ionized outflow in the Circinus galaxy, which range between 0.01 and 0.2 solar masses per year, for example, Konrad et al. And Zihuagn et al. There's also measurements of the molecular outflow from 0.3 to 12 solar masses per year, which is Zihuagn et al. So all these values are consistent, so our inflow value, all these values are consistent with the torus feeding consistent with both the accretion and the outflows. This leads to conclusions. We need very high resolution of milliarc seconds if you want to go directly resolve these scales of the torus. This can be done by both infrared interferometry and sublimated interferometry. Both are very complementary, and what we find at least for the Circinus galaxy, but I think it's now for the super results. We found dense dust in molecular wisps, so that the material is actually inflowing, and we found ionized and dusty bands in outflows, so the direction of the material is being pushed out again. Thank you.
Very nice. You saw this large flow, and you are arguing that means going away in the outflow.
Yes.
But could it stay there and you will start formation and reduce formation? Will it have some signature formation in the region? Because again, in the beginning of talk, the star formation in the clouds, right?
I actually in the cone?
No, I mean, because you said energies that you see in the clouds.
Yeah.
Yeah, you were calculating, you saw inflows.
Yes.
Okay? And the inflows are larger than the additional. It's larger than the black hole.
So then
it's accumulated to form these stars.
Yes, I agree that there could be star formation, and actually there has been this two assumptions, and I think they have done this analysis of the star formation in the years of the Circinus, and there's also some star formation.
Very nice stuff. Very nice data. Outflows are tricky, but inflows are even more tricky. So I think the fact that you have this radial inflow, you guys have a roll doesn't mean that you can take velocity to calculate rates. Because we have from a roll evidence of radial inflow. That's the game works. But you cannot use this radial velocity to calculate rates. Because this is driven by before transformer and those are not radial. So this is an upper limit to the real inflow rate.
Yeah, so that's why actually this if I go with so this 7.5, so essentially this inflow rate here, because this is derived from this radial velocity. So I agree that this is an upper limit, so this is why this results in 7.5. Just taking essentially one arm, where we have this 40 kilos per second, and we keep check, and we see depending on what's the gas molecular ratio, we actually find that we have this 4.3 to 2 solar mass inflow.
So this 90% will be even flatter than that.
No. So
what is it?
Yes, it could be even larger. So it's at least 90%. Sorry.
So at the end, we have more strength than maybe could be able for 100.
But we still need we still need 0.04 essentially. But if we have 7 solar masses deployed, then this is certainly more than just the 80 and the 90% that is being rejected. So it's more on 1%, which is only going to the supermassive. Of what is only in on 10 masses.
Okay, if you have no question, we can.
Yes, I have another slide. Makes advertisements for some movement. I want to make advertising opportunities at least to see this. So there's always the opportunity to collaborate with the staff from so we have also for younger people interested. We have fellowship positions. There's 23 fellowships with around 5 positions coming free every year. Then there's studentships, so you can collaborate with one of the staff or fellows at ISO. And there's 11 PhD positions available, so this is in collaboration with the home stations. People at the master, the bachelor can always come to the internships. And then there's also the possibility for visiting scientists, so it's a place for a large part of this. And then also for very young bachelor students, there's the University Observing School and hands-on observing. Actually, the all was actually recently closed. So yes. And if you want to collaborate, you have me now as people you can contact. You have me, and very soon you will also have James Jeffrey, who is here, be looking at stuff at DC.
Okay, thank you, Konrad. Speaker, we have Falcone, who will speak about spatially-resolved outflow in the Caroline region of this disease. 22 seconds.
Thank you. All right, good afternoon, everyone. My name is Julia Falcone, and I am a PhD student at JWST University, and I'm really excited to be sharing my work today about the multi-phase, multi-scale narrow region outflows in the Seyfert 1 galaxy NGC 3227. So just to get our bearings a little bit about AGN feedback, make sure we're all on the same page, we know that gas accretion to the supermassive black hole results in the expulsion or outflows of gas. And these outflows propagate along a micronical or an hourglass-like geometry that ionizes the narrow line region. So that is what you're seeing, this figure on the left is the hourglass-like structure that is heating and ionizing that gas. And crucially, narrow line region outflows result from the ionization and removal of cold molecular gas reservoirs in the central regions of the galaxy. So what I'm going to be discussing is my study of both ionized and cold molecular gas in this galaxy and what we can learn from it. Now, to briefly discuss our target, NGC 3227, we see that it is this beautiful spiral galaxy here that is currently interacting with a dwarf electrical companion, NGC 3226. And from my first study of this target, as we heard earlier from Marshall's presentation about the development of a bicarbonate structure based on the ionized emission. So this first study was determining the orientation and the extent of the bicarbonate using, here we have ionized O3 emission coming from Hubble WST3 data. And so we were able to determine the orientation, the structure, the extent, the general structure of the bicarbonate for this galaxy. And from that, we were able to learn some really interesting facts about the ionized gas. Namely, for example, we were able to disentangle the kinematics that were present in that ionized gas. And so what we see here is we have our long slit spectrum that is crossing the entire galaxy. And what we're doing is plotting simply the velocity that we derive on the y-axis as a function of position on the x-axis. This green curve here is the rotation curve of the galaxy. And so what we're able to see observationally is the fact that we have these deviations of kinematics from the rotation curve, which indicates the presence of outflows. And in this case, we observe these ionized outflows out to about 700 parsecs at pretty substantial velocities. And then what we can further do with this information, as we heard from my friend Sean Fisher earlier, is use our radiative driving formalism to better understand how exactly these ionized outflows are being propagated. And so just as a reminder, within radiative driving, what that means is that we're quantifying the trajectory of the gas that is utilizing the opposing forces of radiation pressure going outwards and gravity that is going inwards. And so, for example, what that means is when we observe, so all these red dots are observed kinematics. And so what we can do is trace them backwards and say that, for example, when we see these kinematics out to, let's say, almost a kiloparsec at 500 kilometers per second, those data will likely launch from within the innermost 2 to 3 parsecs from the supermassive black hole. And additionally, one more thing that I want to mention here is the turnover radius, which again you heard about in Marche's talk. And now an interesting difference between what we're seeing here and what she presented is that this is a model-derived turnover radius. Again, this turnover radius denotes the distance at which the acceleration of the outflows kind of stops and the deceleration takes hold from gravity. And so this is a model-derived turnover radius, and what Laura was presented earlier was the more empirical-derived turnover radius from her data. And by comparing the model and observed turnover radius, you can better constrain the orientation of the body. So this is a general overview of my first study for HEC 3227, but what I want to spend most of this presentation talking about is my follow-up study, which is now getting into the mass evaluation of the outflows. And so two important questions that we are striving to answer in this study are: one, at what rates are various phases of gas being evacuated from the narrow region? And two, how do these evacuation rates vary with the distance from the supermassive black hole? And so to perform this study, we used 3 phases of gas. First, we used archival data for the CO2 wavelengths. We also used from this some more molecular H2 data at 2.12 microns. And then finally, we used ionized O3 data coming from Hubble and also Spatially-Resolved Observatory, which you heard about earlier. And what this looks like practically is, so we have here our ionized data, and we're dividing it into all of these little rings that are a width of about 11.5 parsecs, which is the spatial resolution elements, thus this for this target. And so we're dividing it up into all of these little areas, and we're also dividing, as you can see here, this is the kinematic major axis of the galaxy. So what we're doing is we're taking some of the flux going this way, some of the flux going that way, so that we can better understand as we go north, as we go south, how exactly the outflows are propagated. And so once we make these, we divide it into all these sections, we can create cloudy models and calculate the gas masses of the ionized gas. So the way that we do that is first, we have our observed O3 and H beta ratios from our long slit data. So again, this is just going from southwest to northeast. What are the O3 and H beta ratios? And then what we do is we generate cloudy models. With cloudy models that range in log U, which is the ionization parameter, and log NH, NH is the hydrogen density. And what we do is for each of these models, as you can see, it's iterating over a distance, the same distance that we have here. And each of the cloudy models results in some combination of this log U and log NH. And this dashed line here represents an observed O3 to H beta ratio at each distance. And so by comparing the observed to model ratios, we can figure out what the best combination of log U to log NH is at each distance. And so from there, we arrive at the plot of, as I just said, log U to log NH as a function of distance. And this is really important because we need these values to calculate the ionized mass. So once we have this, we have the ionized mass at each of these distances that we're calculating. And crucially, we also have the velocity at each of these distances, because for my first study, I was focused on quantifying the kinematics and looking at the different velocities at play. And so what we arrive at for the ionized gas is our ionized gas outflow rates. And so as you can see here, we're seeing outflow rates on the order of peak values of maybe 10 to 12 to 15 solar masses per year. And you can also see that there's an enormous division between the northeast section and the southwest section. That makes sense when we look at how we divide our data, because there's actually a really thick gas lane that intersects NGC 32.7 right around here. And so the fact that we're seeing these really small values is likely just an artifact of that really thick dust. And so, also just to relate this to our conference, you'll remember that the way that Andy escaped prison was by dumping out bits of dirt from his walked out every time he shipped out on the cell block. So in essence, he was transporting material from the nucleus of his cell out to the interstellar medium of the prison yard. And if he wanted to make his life even worse, he could calculate the Spatially-Resolved mass outflows of the dirt around. But I think he was already miserable now. So we can continue onwards with our molecular gas outflows. Now this is actually going to be a little bit different because unlike with the ionized outflows, we know that molecular outflows exist in the nuclear region. So this is a plot from Almudena Montemorero's 2019 paper about NGC 32.7. And so you can see that her and her team clearly marked out areas where there is nuclear outflow from the molecular gas. But crucially, we do not have a sense of how much mass these outflows contain. We only know that it exists, but we do not yet have a quantification of that. Although I do hope to do that in the very near future. And so in order to continue forward with this estimation of the cold molecular gas outflows, we do the same exact thing that we did for the molecular outflows, where we divide it along these 11.5 parsec intervals, divided along the kinematic axis, the northwest, southeast. And so in the solid regions, we have what we believe to be the mass outflow rates, assuming everything that we see from here can be transported or can be converted into outflowing gas. But we also have the shaded, or rather the hatched regions here to indicate that there is a large amount of uncertainty in our results. And so that uncertainty can go pretty far low, but we have an idea of that it's somewhere within this range that outflows exist, but we do want to really nail down the specifics of the cold molecular gas outflows in the near future. So we have our ionized outflows, we have our cold molecular gas outflows. I mentioned also warm molecular gas outflows for the purposes of this presentation. I won't exactly go into it. What I mostly want to get into is our estimation of how exactly the time scales upon which the gas is being excavated. So the main question I want to answer here is how long does it take for the molecular gas in the reservoirs close to the nucleus to be ionized? And so what this plot is showing here is an estimation of that depletion timescale. And so there are a few various little categories here, so we'll go through that. So when we say is maximum, the maximum means that the cold molecular gas is present in the form of outflows. This is our sort of upper limit as compared to our minimum case, where it's a lower limit of there's not really any molecular outflows. And then you'll also see that there is this total transfer or no transfer. What that just means is if we're saying that there is total transfer, we're asking or we're saying that the outflows are carried from one bin to the next. So remember that these outflows are propagating outwards. And so as we move outwards, we have to ask, well, is this mass going to be carried forward, or is it going to be either ionized or redirected in another direction? And so for total transfer, that means that all of the gas is moving forward from one bin to the next. And for no transfer, this is again a lower limit, saying that none of the gas is going from one of these sections to the next. And so what we can see from this plot, actually we can combine this depletion time scale, which asks how long it takes for the molecular gas in the reservoir to become ionized. And what we can do is add on what we call the crossing timescale. So the crossing timescale describes the amount of time it takes for gas to move outwards from its current bin, from its current location, to the very edge of the outflow. So basically how long it takes for the gas to be fully excavated by the outflows. And so what we arrive is our final excavation timescale for an ionized gas, which in total is asking how long it takes for the gas to first be ionized, that's what we see with our depletion timescale, and then move outwards to the edge of the outflows. And so this is our attempt at a novel calculation to really quantify the timescales upon which these outflows have the potential to deplete the full molecular gas reservoirs. And so, also just I want to mention, like, all this actually works logistically. So, for example, let's say around 50 parsecs. And so, if we measure at 50 parsecs, the depletion time scale is somewhere around, let's say, 1 million years, and the crossing time scale is around log 6.3, 6.4. Then it's added together to make a total evacuation time scale of around log 6.6, 6.7, which is to say that each of these evaluations are done on a location by location basis. Because we're dealing with rates, we want to be very careful about how we add things together. And so that's sort of how we learn about evaluating these time scales. And so just to talk about our evaluation time scale a little bit more, because this is the real meat of the project. So from our results, we found that the gas reservoirs can be evacuated on time scales of around 10 to the 6.3 to 10 to the 7.7 years. And the reason why this is important is because the average duty cycle, which describes the duration of continuous AGN activity, is around 10 to the 7 to 10 to the 9 years. And so what we can do is we compare the time scale that we received to the time scale that is generally accepted as the duration of AGN activity, and we can say that our results help to show that AGN-driven outflows are effective in clearing the inner few hundred parsecs of NGC 3227's gas content, and that it may play a significant role in helping to regulate the duty cycle of this AGN. And so that is the primary results of my work. The second paper was just accepted to the Astrophysical Journal, so if you would like to take a look at it on archive, you're welcome to. But the main results are summarized here, and I did not forget the movie. It seemed like a lot of people were talking about movies based on their heritage. I am short and Italian, and so I chose the movie from the king of short Italians, Martin Scorsese. After Hours is a really fun movie about a guy who happens to very bad night in New York City. But I will leave you all with my conclusions, and I will take any questions. Thank you so much.
Very nice. I'm curious to understand and to know how you define the edge of the outflow. Maybe can you elaborate on that?
Sure. So I have, let me see, I sort of have backup slides and I'll just explain a little bit. Okay, so one of the main parts of my first study was determining the extent of the velocity. So for example, where do the kinematics end? And so we did this observation of looking at liquid mirror data where we stopped seeing outflows. And so what we see here, these are the velocity laws that I've derived. And so the velocity law of the ionized data ends at about a few hundred parsecs. So that's roughly how we determined where the edge of the outflows were, but there are also projection effects that can help to significantly lengthen that bit.
The question, in the field slide, you show the critical profile of the instability of the installation. Can
Wait, so you're,
Yes, one of the first.
one of the first slides?
One of the first.
Okay.
And
Or
one of the.
was it like this?
No, after that.
This?
After
Okay.
yes. And how do you estimate the density only from approximately over each iteration? You have some additional information, for example, from software 2 or.
So you're asking how I got this?
Yeah.
Yes. So we take long slit data of NGC 3227 using ground-based Apache observatory. So this is long slit spectroscopy, and so we literally from those measurements we're able to go up and down. The spatial resolution is about 0.27 arcseconds, so it's pretty spatially resolved. And from there, we were able to fit each of these spectra, and from those spectral fits, we were able to get determinations of the flux for the O3 and HBO.
Okay, thank you. We have no other questions. You can get to the again. The next speaker is Iván Ezequiel López, so we talk about the feedback and Low-Luminosity AGN.
Hello everyone. Let's dive in Low-Luminosity AGN. So I am running the desktop between you and Seyfert. So yes, let's go quickly. Yes. I am currently doing a postdoctoral fellowship program. And I'm going to show you some very nice results from JWST in a very nice way. First, I want to do the movie, so you can listen to the talk after. When I was coming to the conference in the plane, I saw one of my favorite movies next to the Shawshank Redemption, so it was easy pick. Nueve Reinas is about two people trying to do easy money during Argentina economic crisis. You know, we have an economic crisis every 10 years, but this is the one in 2001. And it's interesting because it's recorded 1 year before, so you can feel a little bit the mood, the economic crisis coming. So what we care about Low-Luminosity AGNs, so you can see that they are the dominant population of AGNs in the Eddington ratio distribution in the European universe, but also in luminosity functions at all redshift. That is because most of the time a black hole is in the low Hawking phase. I'm talking about 90-95% of the time. Some facts about Low-Luminosity AGNs, we already have some talks, but basically below 10 to the minus 3 of Eddington, the physics change. So forget about the circular kinetics, and you will have more truncated these ADAS and jets. There are some discussions about the structure, but I don't want to take too much time here. But we know some stuff about the feedback. I will focus mostly in low power. They are confined in the host galaxy, and that we know that they can drive outflows, they can displace gas from simulations and from observations. We know that the ADAS wings can also suppress star formation. Travis showed his interpretation of the shocking XM, and Santiago today also showed that they have no gas in the room. But also some Low-Luminosity AGNs can have this high ionization of high velocity outflows, meaning a little bit the classical canonical AGN feedback, but they don't have the strong ionization tones. So if I want to summarize this in one sentence, I would say that the energy release in Low-Luminosity AGNs is mainly kinetic. So our target is M58. It's a massive spiral galaxy Virgo cluster. Its X-ray luminosity is 41, has evidence of an has also a low power radiation that you can see there. And the interesting thing is that because we have low UV radiation field and low power shell, it's a very nice place to study the feedback in a non-standard accretion mode. So this galaxy we studied with the Spitzer. We published a paper last year, and the conclusion that is that we have a radiation that is perpendicular to the plane of the galaxy, and it's inflating this bubble that is expanding and touching the ASM and impacting the dust lanes that we are already in all the region of the impact in the cocoon. The star formation is spread. And the most interesting thing is that the one where nitrogen is the main coolant of the ISF, right? And you can see from this picture, is in green the H2 atoms. That much, the CO and the absorption features from HST. So that was the perfect excuse to get some nice JWST data. With the 3 instrument, we now signed we're 700 parsec in the center, and with a resolution of 10 parsec per pixel. You can see the spectra from the nucleus, from around the nucleus, and it's very nice. There is a lot of features. There are syndicated emission, there are PAHs, there are a lot of H2 lines, there are high emission lines, there are low emission lines. The paper that we published is centering the 44 H2 lines that we detected. And mainly we are like a little showing off all the H2 lines that we detected. And with all these lines, we can constrain the excitation mechanism as we are talking of virus class. In case the notation of H2 is harder than filling a tax form, you can see my notes here. This is the upper vibrational level, the lower vibrational level, and these are the rotational levels that they should follow. They follow selection rules that are key results, not related with wafers. And basically, this is the way that we express. 0, 0 is there is nothing in the vibrational level that's changing, and S1 is the lower excitation that we have in the JWST. And we denote it as 1 for doing a literally short. It could be 1, 0, 1, 1, 2, 1, like that. So let's go to the images. In red, you can see the pH tracing the spiral arm of the galaxy. In blue, you can see the stellar continuum tracing the back of the galaxy. And in green, some dots where feedback is happening. The lower contours here, and the middle contours here, and when we do the zoom to the center of the galaxy, we can see the continuation of the gas lanes here. This is in H2S1, so the low excitation H2 line and the CO. And in the center, you can see a very high excitation line, this is S9, that is tracing this northeast and southwest shock with respect to the center of the AGN. So we can do momentum mass from the H2, and this is just a selection of lines that I will show you. You can see that the dust lanes are very strong, and when we go to higher excitation values, this two-shock region is to loss, we call it, start to appear. The velocity mass, they are between minus 200 and 200 kilometers per second, so nothing crazy there. It's mostly the rotation of the galaxy. There are some things going on there that we can show you after. But when we go to the dispersion maps, we can see that there is lower dispersion in the last phase and a little bit higher dispersion in the other parts. So let's talk a little bit of the results. We can do H2 mass with all the ratios of the lines that we have. So these ratios trace the temperature, the station temperature of the H2. And you can see that the dust lanes appear again. You have the two dots right here. When we go to higher ratios, so S9 or S5, we are tracing the hotter part of the H2, and you start to see that these lobes start to show some structural absence. We did some operations with models, and the only models that they reproduce our ratios are the C-type shocks of low densities and low velocities, where we are talking about 10, 40 kilometers per second. And if you ask me what these controls are, these controls are the orthogonal ratio of the H2 that should be 3 if we are in equilibrium conditions, and we have the values in these controls of between 1.5 and 2.5 that suggest non-local equilibrium or recent transformation. So what we can do with all these H2 lines, we can model excitation following a distribution in the temperature using the model of Low-Luminosity. Because Low-Luminosity developed their model for Spitzer, what we are doing is introducing this new term that is a cutoff near the H2 dissociation temperatures, because we are right with 18, that is much closer to the dissociation temperature of the H2. We can feed that spatially with this beautiful maps on the power flow index, that is the presentation of this, that is red values, blue values, trace hotter H2 gas, that is, of course, in the center near the nuclear, and all the contribution in the center, but also there is a lot of hot gas in the gas elements, right? And when we go to the masses that we can trace with this model, you will see the controls are the CO, so the polar phase. These are the masses of the from 200 Kelvin, and you can see that we are of course tracing all the gas lengths, but also we are tracing a lot of reservoir of H2, warm H2 in the center that they show the distribution of the loss. So what I was telling you is that for each spacer we are tracing the thermal model, the pure thermal model is this one, and you can see right here the raw vibrational lines. They are systematically below the thermal models. So the first thing that we did was to explore other excitations for the vibrational lines, and you can see this plot here where we compare the X-ray heating, UV heating, and other thermal processes, and our regions in the galaxy are always consistent with shocks, and maximum is between 10 and 30% of this non-thermal excitation. So other modes have not explained this, but after we remember that the vibrational lines they have higher critical densities, right? And because we are working with low density shocks, the collision cannot sustain the thermal regulation, and that's why they have this subthermal excitation. After we started to discuss what is driving the H2 excitations, and we separated the thermal mechanism from the non-thermal mechanism when we compare with other potential candidates in the galaxy, so shear power, the X-ray heating, and chemical conditions from all the inflows and outflows. So there are examples of the study in 2009, and we assume conservative efficiency, or you can see that only the shape is the one that can explain the H2 luminosities from the center of the galaxy to the 2 kilobars. The only one that is comparable is the total collision, but just very far away of the center of the galaxy in 1.5 kilobars. For the non-thermal mechanism, so assuming that this 10-30% is the non-thermal, UV pumping, X-ray pumping, and X-ray cosmic ray excitations, and the only one that we can produce is the X-ray photons, because the luminosity is 41 and is pretty strong. And this was already observed in units. So I want to go quickly for the kinematics. So I told you before that the velocity fields were dominated by rotation, and you can see here the channel maps. This is the shape axis, and you can see that there is no disturbance in the shape axis line. But you can see that here the northwest and southwest structures appear. And if you see the PV diagrams, here the colors are the CO21, and the controls are the lower excitation line of H2, and this one is colors and controls are X9, so higher excitation. You can see that the lower excitation follows pretty well the dust length and of the galaxy, but there is something going on in the northeast, and we want to higher resolutions that because the field of view of Newton is a little bit short, so when we don't trace this region, we see that very clear morphology that aligns with this, and what we interpret it as the flowing gas is going from the C-type shock, right? If you ask me for the velocities, the projected velocities of these outflows are around 300 kilometers per second, so again, nothing crazy, nothing 1,000 kilometers per second. But I think the most interesting result is that when we see, we compare the data of the JWST with HST, you will see here the star formation rate that you can see from the UV. That was detected in the HST like 20 years ago, and you can see that our shock edge duration lies just between the UV emission, and that would lead to possible compression and positive feedback of this area. And when you see the spectra in these regions where the disk is a little bit disturbed, you will find these double horned lines. And this line, for example, is 1COS3, this is 1COS2, this is 1COS1, this is S11, S10, S9. So very high station lines for H2, and you can see these double horned lines that would be the interaction between the dense formation material of the ring with the low density of flowing gas that are causing these instabilities. So these are my conclusions. If you are interested in this galaxy, we are also now working on the Iris gas, the dust, to reveal the impact in the star formation. But if you want to take away home message, whatever, is that this gentle feedback shock, the ISM in the kiloparsec scale is suppressing the star formation there, but after the kinematics is only leading to happen. I have some open questions for you. How common is this type of feedback in low-luminosity AGN, and even larger luminosity population? What is the role in galaxy solution that I'm interested in trying to get some answers? So if you're also interested, please contact me. Thank you.
Thank you, Iván, for the brilliant talk. It paints a very different situation with respect to the ionized gas produced by highly accreting greenhouse and Zihuagn, typical Zihuagn. So, question for Iván.
The people want to see the darkness.
So, don't be shy. One question.
Yeah, so this is really good. We're talking several others during this meeting. Gives me hope that there's a way to quantify the role of kinetic, so-called kinetic energy. This gives me hope because I don't quite know how to do it. This is the beginning of a possibility. So this session takes exactly on this. So how do you turn this into especially some kind of time scale? And this is of course a simultaneous explaining. So if you can estimate the amount of energy, kinetic energy implied by those shots, that's the first step. You have a model derived from shock velocities. Some amount of material because you have some kind of strip. And the next thing I like to know is what time scale this is operating. You can do that and you have some integral. And that would be really helpful.
Okay, so talking about the time scale, is the low auto-vibration values that we are seeing comes from recent age information that indicate this type of scale in the 200 parsecs region, right? That is where we are measuring the low auto-vibration value. Another thing that we discussed in the paper is that in blue here you have Paschen alpha. And you can see that the Paschen alpha doesn't align very well with the star formation really. So that could be that can we talk a little bit about the age of the stars, right? So you can have like young stars that they are not actually forming new stars because they give their passion for that. Because we also have very nice Newscape data. We are trying to fit in the stellar population of that region to go deeper in that interpretation. And the other thing that we were saying, that the Doppler effects, right? How much this kinematic field is acting. Right now, we are trying to calculate the kinetic energy with the H2 masses and try to do something similar for the gas to try to derive some efficiency, coupling efficiencies.
I was also like biform H2 profiles that you showed.
Yes.
How no, the biform.
I'm sorry, yes. Here.
Your interpretation about the feedback, can you explain that as well?
Yes, so basically the difference of the two peaks of the lines is around 100 kilometers. And here you have the bipolar profiles appear here, 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 and here. So they're like in different places. These two are the stronger ones that we are showing. And they're just outside like the short regions in the edge when you interact with this higher dense material density from the star formation rate. So when you have the interface of a dense material with a low dense material, you can have some like radical or instabilities, and that will produce this type of environment profiles. But we didn't want to visualize the error.
Okay, right now, there, another question.
Thank you for something. Can you hear me?
What?
So just wondering, I know there's a lot of information just missed it, but did you look at the randomness of the galaxies with those, like, because you get to the point where you start programming the scales of levels to show the star region.
Yes.
You've got a job good angle. Did you have a look into the alignments of the H2?
The line?
The line widths.
Yes, of course, we are modeling. These are the velocity curve of the H2, right? So there is nothing higher than 400 kilometers per second.
Thank you very much.
Okay, whether we take Iván and what is maybe an announcement about